deploying an MCP server is only the starting line. The real test comes under load, slow tools, shared dependencies, failures, and growth. In this topic, we'll turn "it works" into "it holds up." So far, you've built the foundation: how MCP works, how to secure access, and how to design reliable tools. You've also seen deployment and observability. Now we'll focus on the operational pressure points: keeping production MCP servers fast under load, scalable as demand grows, and resilient when dependencies fail. Think of MCP performance as an end-to-end request path, not a single server metric. A tool call moves from the client through authorization, validation, tool execution, downstream systems, and response shaping. Any stage can become the limiter: a database, a policy check, a queue, or a slow external API. Scaling is a balancing act across latency, throughput, cost, and reliability. But production optimization has guardrails. We cannot trade away tenant isolation, meaningful authorization, or audit trails just to make a request faster. Most MCP latency comes from a familiar set of causes: slow downstream services, costly database or search queries, long-running work, large payloads, cold starts, and concurrency limits. The good news is that these are measurable patterns, not mysteries. Once you can see them, you can isolate and improve them. Before optimizing production tools, measure what is actually happening. Averages are not enough because user pain often lives in the tail: P90, P95, and P99. Track each tool's request volume, duration, errors, timeouts, retries, cache hits, and queue depth. Then break latency into stages: authentication, validation, business logic, downstream calls, serialization, and network transfer. That shows where time is really being spent. Finally, define SLOs for critical tools, especially the ones agents depend on. Optimization becomes a targeted engineering decision, not a guessing exercise. MCP tools often sit between the client and systems they do not control, so assume some dependency will be slow. Give every downstream call a clear timeout budget, and fail deliberately instead of letting the whole request hang. When calls are independent, run them in parallel, but cap concurrency so you do not create a new outage. Cache stable data when permissions and freshness allow. And when a dependency is unavailable, consider returning a partial answer with the limitation clearly stated. The goal is predictable: honest behavior under pressure. Expensive search tools often fail because they let the model ask for too much. A production tool should force the query into a narrow shape, require tenant scope, meaningful filters, limits, and pagination before any large search runs. Build indexes around the access paths the tool actually uses, including authorization predicates, so you do not fetch first and filter permissions later. Avoid generic search everything endpoints. They create slow scans and huge responses. When a costly result does not need live freshness, pre-compute it or materialize a summary. When an MCP tool may take minutes, don't hold the request open. Turn it into a job. The tool accepts the request, validates inputs, stores the work, and returns a job ID immediately. Behind the scenes, a queue or workflow engine handles processing, retries, rate limits, and load smoothing. The client then polls or subscribes to notifications using that job ID. Status should be explicit: accepted, running, completed, failed, or action needed. When processing finishes, the client retrieves the result from storage. This keeps the experience responsive while backend work completes safely. Oversized responses are like overpacking for a short trip. Everything technically fits, but the journey gets slower and harder to manage. In an MCP server, large payloads increase latency, memory use, token cost, and client reasoning effort. Shape the response before sending it. Page results, filter aggressively, and let clients request only the fields they need. Return summaries and structured records, not raw dumps. When more data is available, include a cursor or continuation token. For large files or artifacts, send a resource link instead of the whole object. In production, response time is shaped by deployment behavior as much as by code. A cold start means a new MCP server instance is doing setup before it can help, loading configuration, opening connections, and warming caches. Concurrency limits act as guardrails. They prevent bursts of tool calls from exhausting CPU, memory, database pools, or downstream APIs. Auto-scaling helps, but only when triggers reflect real pressure. Request rate, call duration, queue depth, and dependency saturation. Capacity planning should replay realistic agent workflows, because chained tool calls create very different load than isolated benchmarks. Caching is powerful, but in an MCP server, it can become a security boundary. A cached answer is safe only if the key captures who is allowed to see it. Include the tenant, user or role, scopes, tool name, input hash, policy version, and any parameters that affect authorization. Do not cache only by query, URL, or prompt. That can leak one tenant's result to another user. Choose the caching layer deliberately. Tool output, API response, database query, summary, or metadata. Then add TTLs and size limits so stale, poisoned, or oversized entries do not persist. Production caches need more than a TTL. They need a contract. Every cached response should tell consumers how fresh it is, using fields like generated at, cached until, source version, or a freshness status. For critical changes, do not wait for expiry. Permission revocations, tenant deletion, and revoked access should trigger event-driven invalidation immediately. Match TTLs to risk, short for sensitive or fast-changing data, longer for stable reference data. Be selective about what enters the cache at all. Secrets, tokens, personal data, and policy-sensitive decisions can turn a performance optimization into a leakage incident. Put a clock on the whole request. If the user-facing limit is 2 seconds, divide that budget deliberately across authentication, validation, database work, external calls, serialization, and a safety buffer. Each downstream call needs its own timeout, so one slow dependency cannot consume the entire request. Retries help only when the operation is safe and the failure is likely transient. Keep attempts limited, use exponential backoff with jitter, and stop when rate limits, circuit breakers, or cancellations say stop. Finally, make every timeout and retry visible in logs, traces, and metrics. Failure handling is about containing damage before it spreads. A circuit breaker watches a dependency and stops calling it when failures cross a threshold. Later, it probes recovery in a controlled way. Bulkheads separate capacity, so a noisy tool, tenant, or service cannot consume every worker. Queues smooth bursts by turning immediate pressure into managed background work. Fallbacks keep the user experience useful when the ideal answer is unavailable, using cached data, partial results, or a clear retry signal. Together, these patterns turn dependency failure from a system-wide outage into bounded, observable degradation. Scaling MCP servers comes down to discipline. Measure real bottlenecks, bound expensive work, cache only when it is safe, and isolate failures before they spread. Most production problems are predictable, from slow APIs to saturated concurrency. Next, we'll apply the same mindset to versioning, governance, compliance, and incident readiness, so systems degrade gracefully instead of failing chaotically.